Right, chapter 19, magnetism. So we finished electricity, now we are in magnetism. So what do we have in magnetism? These are the contents. Looks like too many contents, but it can be just most of them just description. We can go a little faster. We will start with introducing magnets. You have seen magnets, bar magnets, which has two poles, north and south. Then we will find that Earth itself has its own magnetic field. That's why the compass shows the direction of the magnetic north. And then we will, see a magnet will create magnetic fields around it. So we'll study the magnetic field. Number 4, we will see that, when a charged particle moves in a magnetic field, it will be affected. It will experience a force, which is called the magnetic force. A charged particle, if there's an electric field, it will feel an electric force. Similarly, if the charged particle moves, only when it moves, not otherwise, in a magnetic field, it will experience a magnetic force. Number 5. So current carrying conductor mean what is current? Charges moving. So in a current carrying conductor, in a wire, those are charges moving. So the wire itself will feel a magnetic force if the current carrying wire or a conductor is kept in a magnetic field. It can also experience a torque. Torque is a couple of two forces, trying to rotate it. One force even, okay. Force can make something rotate. So we can have such a thing when you keep a current carrying circular wire in a magnetic field, it will experience a torque force that is trying to rotate. So that is a torque. Torque is a tendency of a force to rotate something. So we will discuss that in number 7. That will lead to motors and so on, electric motors. Then you have this Ampere's law, which gives you the magnetic field due to current. Okay, that's a law that tells you how we can get the magnetic field due to a current carrying a current. Number 8. Then we will see that when you have two conductors carrying current, say keep them in parallel, they will have magnetic force between them. Sometimes it will be attractive force, the wires going to come closer if they are in the same direction. If it is in the opposite direction, then it will be repulsive force. We will see how that happens. Number 9, we will see the magnetic field generated by current loops. A wire loop which has a current inside it, then we will have a magnetic field due to this current carrying loops. Solenoid is when you have more than one loop, like a spring. Okay, we have a wires wound like a spiral, that is called a solenoid, and from that we can have magnetic field. Finally, magnetic domains. Then we will see how a permanent magnet is formed. You have seen permanent magnets, like a iron piece of iron which is permanently magnetic. So we discuss how that happens in these magnetic domains. Right. So a bit of introduction here. Magnetism is one of the most important fields in physics. So there are many applications. Okay, like even the memory in a computer, hard disks, they all utilize the magnetic field. The magnetism is actually very much linked to electricity. They are not really something different. Okay, magnetic field can be shown as electric field can be shown as magnetic field. Magnetic fields affect moving charges. It will produce a magnetic force on moving charges. Moving charges, on the other hand, can produce magnetic field. A current carrying wire will have magnetic field around it. Then we also see that, when the magnetic field changes, it can create electric field. So they are very much interconnected. In fact, you can say that magnetic field is another manifestation of electric field. This person, James Clerk Maxwell, he first described the unity between electricity and magnetism, and that's a famous equation, Maxwell's equations. There are 4 equations which unite both electricity and magnetism. So this happened in the 19th century, the early 19th century. So that's why we have something called electromagnetism, because they can be united together into one. Instead of saying electricity separately and magnetism separately, you can call electromagnetism. Right, now the topic 1 about magnets. You all seen magnets, right? In the lab you have something like this. One is the north pole of the magnet and the south pole of the magnet. So unlike electrical charges, we can have them separate. We can have a separate positive charge and a separate, that's also some kind of polarity, positive and the negative. We can have them separately. A charge which is entirely positive, something entirely negative. Can you have it with magnets? Can you have entirely a north pole only and only a south pole? No. So far, no one has, we call monopoles. Monopoles do not exist. Well, theoretically, it is possible to have monopoles, but no one has ever found a monopole. Right. So the properties of this magnet, if you bring another magnet with the north pole opposite to the north pole of this, what happens? They will repel. Like charges, when you have like charges, positive and positive will repel. Likewise, north pole of a magnet and another north pole of a magnet will repel. They will push each other away. But what if we bring the south pole closer to the north pole? Then it will be attracting. Okay, the south pole and the north pole, unlike poles, will attract. Like poles repel, and unlike poles attract each other. It is somewhat similar to the electric charges, positive and positive, or negative and negative will repel. Similarly, north-north or south-south will repel, but north-south will be attracting. Something different from the electric charges is this, so you cannot have monopole. Say you take a magnet and you break it into half. What happens? One half will become another magnet with both north and south pole. And the left side will become here, will be south, because already have a south, this will become north. So when you keep breaking, we will never manage to get only north pole. It will always be, no matter how small it becomes, one side will be north pole, the other side will be south pole. We can take an unmagnetized piece of iron, okay? It has to be a magnetizable material. Iron is magnetizable, okay? So you take a piece of iron which is not magnetized, and you can make it magnetized by stroking it with another magnet, which is already a magnet, and something is not a magnet, a piece of iron. You can bring it close and stroke on it, okay? Touch repeatedly, stroke on it repeatedly, it becomes a magnet. So it is somewhat like, the charges, you can make the magnet by touching, right? Charging by conduction. Then you can also induce magnetism, like charging by induction. You can have charging, magnetizing by induction, induce. You don't really have to touch, you can bring it close, a permanent magnet. Say this is a magnet, and something is not magnet, keep it close. Eventually, this will induce magnetism on that. Only magnetizable material like iron can be magnetized that way. Strong permanent magnet, keep it close, and that one will also become magnetized. There are two types of magnetic material. Soft magnetic material, iron is an example, that can be easily magnetized. So we call it soft magnetic material. At the same time, it can lose its magnetization quickly. Easy to magnetize or easy to lose. This type of magnetic material, example is iron, are called soft magnetic material. The other type is hard magnetic material. They are difficult to magnetize, but once you get it magnetized, it will retain its magnetism for a longer time. It will not get easily demagnetized. That is called hard magnetic. These type of materials are called hard magnetic materials. Okay, now where is the magnetic field coming from? The source is actually because of the moving charges will induce a magnetic field. If you have a moving charge, okay, the space around this moving charge will have a magnetic field. If a charge is not moving, it will have electric field. Okay, it is there anyway. You learned that before. Electric field is from electric charge. But magnetic field from a moving charge, electric charge. The region of space surrounding a moving charge will have a induced magnetic field. So we will have a charges will be already know it has electric field, but magnetic field will come from a moving electric charge. And a magnetized magnetic material, you see the bar magnet is not moving, right? It is in the same place, but you get magnetic field around it. You can explain it. We can say that inside this magnetic material, we have moving charges. We'll come to this explanation later. But you can either have a magnetic field from a current. Current is what? Moving charges, right? So around this wire, current carrying wire, you can have magnetic field. Also, we can have a magnetic field from a bar magnet. Apparently, it is not moving, but the atoms of the molecule inside, they will have what is called the magnetic moment due to the spinning atoms and so on. We will explain that later. So magnetic field come from a permanent magnet, a magnetized magnetic material, or from a current carrying wire. So magnetic field is a vector. I mean, it has direction, like electric field has a direction. Magnetic field also has a direction. We give the symbol B for magnetic field. Magnetic field, the symbol is B. What is the symbol for electric field? Anyone remember it? Field. That's current. Current is not electric field. Capital E, I think. Capital E. Okay, capital E. Electric field is capital E. Magnetic field is capital B. Well, electric field, the words start with E. So electric field is E. It's also a vector. Magnetic field is the symbol we use is B. Now we kind of an idea where like magnetic field, if you have a permanent magnet, there is a magnetic field around this magnet. But we still don't know, what it is, okay, how we can measure it. So we are coming to that. The direction of the magnetic field is given by the direction of the north pole of a compass needle. You know what is a compass, right? Compass. In your mobile phone, you have the compass app, for example. It can show you the direction of the magnetic field. And you use the compass for the direction of the Earth's north pole, right? Don't confuse them. Earth has a geographic, if you take the Earth, there's a pole, it is spinning about its axis. The North Pole is here, and the South Pole. That's a geographic North Pole. But the Earth also has a magnetic field, and it's magnetic north and the magnetic south. We will come to that later. But here, how do you get the direction of the magnetic field direction? It is the direction the compass will point. It will point in the direction of the magnetic field. Hopefully, I hope you have seen a compass. They use it to get the direction. So what happens is the compass needle will point in the direction of the magnetic field, and Earth has a magnetic field. So if there are no other magnetic field around, so the compass will point in the direction of the Earth's magnetic field. And we can use magnetic field lines like we do with electric field lines. We can also have magnetic field lines that can show the magnetic direction of the magnetic field. So we can use these compasses to trace the magnetic field lines. So for example, here we do it with a bar magnet. Bar magnet come with the North Pole and the South Pole, and we keep several compasses like that in several places. So here the compass will be pointing like this. Here the compass will be, let's say, pointing like that. So we can trace them, and that will draw the magnetic field line. So you can see at the North Pole of the magnetic field lines will be coming out. At the South Pole, the magnetic field line will be coming inward. So at the North Pole, the magnetic field will be outward. At the South Pole, the magnetic field line will be coming in. So we can place many such compasses, and thereby can we be able to draw the magnetic field line. So this is the magnetic field line from a bar magnet. So at the North Pole, magnetic field line will be outward. At the South Pole, the magnetic field line will be coming in. It is somewhat similar to the North Pole is like the positive charge. Electric field line at the positive charge will be going out. Electric field line at the negative charge will be coming in. So at the North Pole, the magnetic field line will be going out. At the South Pole, the magnetic field line will be coming in. So this is by definition is how we should draw the magnetic field line. It will be such that at any point the tangent to the line, magnetic field line, will give you the direction of the magnetic field at that point. There are experimental ways to kind of visualize the magnetic field line using iron filings. This word filing, ing, is, filing means sawing. I mean, you can get dust, iron dust. So we can call it iron dust. Instead of filings, you can call iron dust. Small, like a powder, iron dust, if you have them, because iron is magnetizable. So if you sprinkle this dust on a bar magnet, they will fall and make this pattern. So because it will show you the magnetic field line. So it is at the poles, there will be a lot of the strength of the magnetic field will be greatest. So you will gather more iron filing, and you will have this kind of thing forming. So it will kind of is tracing the magnetic field line. You don't know the direction, by this experiment, but if you know where the North Pole is, then from the North Pole it will be out, and at the South Pole it will be coming in. That will be the direction. The magnetic field will align, or the dust will align itself along the magnetic field lines. Here we have another example. This time not one magnet but two magnets. We need to do that. Then one of the magnet, north pole, is here. The other magnet, the south pole. So you are facing the north to south. When you sprinkle this iron dust, just throw it at this, then you will see the magnetic field lines forming. So from the north, it will go to the south. So it will look like this. You can draw a parallel between this and the charges, right? So north pole will correspond to the positive charge, and then south pole will correspond to negative charge, and you will have the electric field line forming in a similar manner. So this is not electric field line, rather it is magnetic field lines. So another one, what's the difference? We had north and south. Here this is north and north. So now what happened? The magnetic field from this guy and this guy at the middle will cancel. So there will be no magnetic field in the middle region. So from both, the magnetic field line will be going out. Again, you can draw a parallel between a positive and a positive charge. The electric field line will be something similar. Electric field in the middle area will be 0. And as you go closer to the charges or the poles there, the magnetic field becomes stronger. It will be same here with the north pole and the north pole. And similar thing, you can do it with the south pole, and negative charge and negative charge. Right, so that finishes the introduction, the first topic, which is magnets. Okay, we understand magnets and we draw a parallel between magnetic poles and the positive charge and the negative charge. So you can remember it by thinking of the north pole as the positive charge and the south pole as the negative charge. Okay, number 2. Magnetic field from the earth, earth's magnet. Please put your phones away and pay attention here, close here. You can see the screen here. Earth spin about its axis, right? It has a spin about a certain axis, and one where the axis at the top we call the north pole, and this is the south pole. These are geographic north pole. Don't confuse that with the magnetic poles. So Earth is spinning about its axis. So where at the top is the north pole, where the spinning will be 0, because this is spinning about this axis. At the equator, you will be describing a big circle. At the north pole, if you are sitting at the north pole, you are just spinning in the same place, right? If you are at the equator, you are making a big round. If you are at the north pole, so that's what we mean by saying it is spinning about this axis, and the north pole here and the south pole here. When there is a magnetic field from the earth itself, it is as if we have a giant magnet buried inside the Earth's core, and here we have the magnetic south, and here we have the magnetic north. These poles almost close. I mean, for example, the Earth's geographic north pole corresponds to the magnetic south pole. Not exactly at the same place, there's a small shift, but it is very close to the Earth's geographic north pole is close to the corresponds to the magnetic south. So what will happen now, you will have a magnetic field like this from the magnetic north pole and going to the magnetic south pole. So this is Earth's magnetic field. And the Earth's geographic south pole, that is this one, corresponds to the magnetic north pole. So there's a flip, okay? North corresponds to the south magnetic and geographic south corresponds to the magnetic north. So here is a better picture. So we can imagine where is the magnetic field of the Earth coming from. We can say, oh, there is a magnet inside, and its south pole of the magnet is closer to the geographic north pole, and the magnetic north is corresponding to the south geographic pole, and we will have a magnetic field like that. So this is the Earth's magnetic field. But it's not really there. We can, it's a model, okay? We say, okay, why is this Earth's magnetic field? We can imagine there is a big bar magnet buried inside the Earth, and that is providing the magnetic field. It is not the right picture, but anyway, for the time being, we can imagine it like that. Then, if you take a compass and say you are in the equator, somewhere in the equator, if you take a compass, the compass will be aligned in the direction of the north, right? Because the north geographic pole corresponds to the south magnetic pole. So what happens if you bring a compass and say this is the Earth's north direction, the geographic north, and the compass will be pointing like that. So that tells you the Earth's magnetic field is in this direction, and also it is telling us the direction of the geographic north, okay, because happens to be coinciding with the south magnetic pole. And if you move towards the north, okay, I mean geographic north, suppose you come here, Riyadh, for example, is it along the equator? No, right? It is above the north, not above the north. So if you come, suppose you are in Riyadh, actually the direction of the magnetic field will be not parallel to the Earth, it will be tilted. But when you take a compass, the compass cannot go like this. It can only rotate horizontally. So it will be pointing horizontally, but if you allow it to rotate, say it is free to rotate like this, it will not stay like that, it will dip down. If you are in Riyadh, the direction of the magnetic field will not be horizontal, it will be slightly down. This angle of tilt is called the dip angle. So we are coming to the dip angle of the Earth's magnetic field. If the compass is free to rotate vertically as well as horizontally, it is not going to in Riyadh, because away from the equator. In the equator, it will be horizontal, but if you are away from the equator, there will be a dip. The angle between the horizontal direction, and the direction of the Earth's magnetic field is called the dip angle. So in Riyadh, there is a dip angle, but if you are in the region which is in the equator, the dip angle is 0. Farther north, the more you go towards the north, the farther from the horizontal the compass needle would be. It will be dipping more and more. And where the compass needle will be at the equator, the dip angle will be 0. And if you go very close to the south magnetic pole, then it will be dipping straight down 90 degrees. The dip angle of 90 degrees is found somewhere in Canada, a place called Hudson Bay. Maybe it's a sea region, so it's a bay. So now you know where the Earth's magnetic south is. It is not exactly at the North Pole, but it is somewhere off in Canada. The magnetic and geographic poles are not in the same exact location. So the difference between the true north mean geographic. We are talking about the geographic north and the geographic. Okay, let's see. This is here. He's talking about the true north, which is the geographic north pole, and the magnetic north. The difference between the true north, geographic north pole, and the magnetic north is called the magnetic declination. So you have another concept that you should understand. We introduce what is dip angle. Dip angle is the angle between the horizontal and the magnetic field direction, actual magnetic field direction. And then we have another term, which is the magnetic declination. This is the difference between the true north at the geographic north pole and the magnetic north is called the magnetic declination. Because if you use a compass to find the north direction, it is not really pointing to the true north. It is pointing to the magnetic south pole. So there is a difference between the true north and the magnetic south pole. So we call this difference as the magnetic declination. Right, now, where is this magnetic field coming from? From the Earth. We said it is coming from the magnet that is buried inside. But that's not true, right? You cannot have large masses of permanently magnetized material, if it is the bar magnet we call, buried inside. It is not possible because, as you go into the Earth, the temperature increases. It becomes very, very hot. We are talking about thousands degrees and so on. At this temperature, it will melt everything. We actually have a liquid core inside the Earth. It's a liquid. Even metals will be melting. So it cannot have such a permanent magnet. So the most likely source of the Earth's magnetic field is electric currents in this liquid part of the core. So the Earth is spinning, right? The Earth is spinning. So the liquid also going to spin inside the core. So this liquid consists of charges. So charges are moving. Okay, there will be separate charges that are moving. The charges also will be spinning with the Earth spin. So this is a current. So current produces, so moving charges produce magnetic field. So that is the source of Earth's magnetic field, not a bar magnet kept inside the Earth's interior. That's not possible because they will melt. And also there are some facts about this Earth magnetic field. The direction of the Earth magnetic field reverses every few million years, million, like 3 million years or 2. It reverses the direction. Not the spinning axis, okay? Spinning, we are not talking about the spinning axis. We are talking about the magnetic north and the magnetic south. If you were living, say, 3 million years before or something like that, and the Earth's magnetic north is in the direction of the current magnetic south. It is flipped. How do we know that? There are evidence from the basalts. Okay, when volcanoes erupt, what is volcano? Right? From what is inside the Earth, things come out of the volcano. So the volcano deposit, activities of the volcano activities from the past, we can observe them. And from that, there is evidence to show that the magnetic north-south is reversing every few million years. But our lifetime is like, 100 years maximum. So you're talking about millions of years. But how do we know? Because we don't know. I mean, no one could tell you about what happened 2-3 million years before. But scientifically, by studying these basalts or the lava or whatever that is resulting from volcanic activity, we can deduce that. Why this reversal happened? It is not understood. We don't really know. There is no proper theory for explaining that. The section 3. So we are talking about magnetic field. When you keep a charge in a magnetic field and make it move or give a certain velocity, that charge will experience a force. And when the direction of the velocity is perpendicular to the magnetic field, the force will be maximum. When the direction of the velocity is parallel to the magnetic field, the force will be 0. In between the 0 and 90, we'll have in between value. So people do experiment and they figure out this formula for the magnetic force. So you can see when the Q is high, force will be high, linearly proportional. When the speed is large, force will be large. When the magnetic field is large, the force will be large. And the sine theta term will explain its dependency on the angle between the magnetic field and the velocity. So if the velocity is parallel to the magnetic field, no force, because theta equal to 0, sine 0 is 0, that will make the force equal to 0. And as expected, when theta is equal to 90, when it is moving perpendicular to the magnetic field, theta is 90, sine 90 is 1. So you get the maximum value for the force. So remember, what is theta? Theta is the angle between the velocity vector and the magnetic field vector. And also you should bring the force vector and the velocity vector tail to tail. Okay, you should bring tail to tail, and then you talk about the angle. The angle is the angle between them, the small angle between them. So somebody can say, what about this angle? That is also angle between E and F. We are not FB, magnetic field. So magnetic field vector and the velocity vector, the angle between them, the smaller angle, when you bring them tail to tail, that is the angle theta. And the force is given like that. And I can rearrange to make the magnetic field as the subject. And I can say the magnetic field B is equal to the force, magnetic force that is felt on the charge, divided by the charge, multiplied by the velocity of the charge, multiplied by the division in the denominator. Sine theta will give you the magnetic field. So we can use this equation to get the magnetic field. So you can take a charge, a known value, and give it a certain velocity and make it move in a magnetic field. And we know the direction between the angle between P and B. Measure the force acting on it. We can measure the force. Then I can use this equation to determine the magnetic field. What about the unit for this magnetic field? From the equation we have for the magnetic force, we can get the units. F will be measured, SI unit is Newton, Q is measured in Coulomb, and velocity is meter per second. Sine theta has no unit, it's dimensionless. Theta is measured in radian, and sine of theta again will have no units. Radian is dimensionless because it's a ratio of length to length. So if you combine the Coulomb per second, that will be ampere. So I can say the SI unit for magnetic field is Newton divided by ampere meter. But as it happens, we don't want to say a big name for the unit, Newton per ampere meter. We shorten it and call it Tesla. Tesla is nothing but Newton per ampere meter. But we call it Tesla. So if someone asks what is the SI unit for magnetic field, the short answer is Tesla. And the symbol for Tesla is capital T. Tesla is a scientist name, who work on this electricity and magnetism. So to honor him, we use his name, Tesla, as the SI unit for magnetic field. Tesla is usually a big unit. Okay, if you have 1 Tesla of a magnet, that means a big value. Okay, so highly magnetic material. So we introduce a smaller unit called Gauss. 1 Gauss is 0.0001 Tesla. Why we need this? Because the Earth's magnetic field is not 1 Tesla, it's very small magnetic field. So it is about 0.5 Tesla, that means 0.00005 Tesla. So that's why sometimes we use the Gauss for measuring the weak magnetic fields. In a lab, you can have a very big magnet like 2.5 Tesla. Okay, the magnetic field from a small bar magnet will be much less than 1 Tesla. Earth's magnetic field, for example, superconducting magnets. Sometimes we need a very strong magnet. Like in an MRI machine in a hospital, they need to magnetize these protons inside our body. So that's why we make measurements. That needs a very high magnetic field. We get it through superconducting magnets. This can be as high as 30 Tesla. Okay, that's a very strong magnet. Earth's magnetic field, on the other hand, is this much Tesla, which in terms of Gauss, it will be 0.5 Gauss. Now, how do we get the direction of the magnetic field? We can measure the magnitude by using this equation. You measure the force, then we can get these values and measure the strength of the magnetic field. But what about the direction of the magnetic field? Experiment shows the direction of the magnetic field will be magnetic force, not field. The direction of the magnetic force will depend on the direction of the magnetic field and the velocity. It will be perpendicular to both of them. The magnetic force that a charge experiences when it is moved through a magnetic field will depend on the direction of the magnetic field and the velocity of the charge. It will be perpendicular to both. So let me demonstrate using this my pen and the remote. Imagine a charge is moving in the direction of this pen. Okay, so this is the red arrow here is the direction of the velocity of the charge. And the green arrow, let me use the remote for the magnetic field. So this is the direction of the magnetic field. So charge will now experience a magnetic force. What is the direction of the magnetic force? It will be perpendicular to both of these. So if these two vectors, velocity and the magnetic field, define a plane, like, you can imagine this plane, this yellow thing. So I'm going to keep it horizontal like that, the plane formed by these two things. The magnetic force that is experienced by the charge will be perpendicular to this plane. Why? Then only it will be perpendicular to both magnetic field and the velocity. So it could be either vertically up or vertically down. If I say this is in a V and B are in a horizontal plane, so the magnetic force can be either up or down. Both are perpendicular, right? If the force is this way, it is perpendicular to both magnetic field and the velocity. If it is down also, it is perpendicular to the velocity and the magnetic field. Which is the correct direction? Is it up or down? This we determine using what is called the right hand rule. So you take your right hand and put your fingers, right hand fingers, except the thumb, along the velocity direction and curl your fingers towards the magnetic field. Then the thumb will be showing the direction of the magnetic force. So put your fingers in the direction of the velocity, and then you should be able to curl your fingers toward the magnetic field. If you keep your finger like this, can you curl it towards the magnetic field? No. If you keep any other direction, no. You have to keep it like this. Then you'll be able to curl it towards the magnetic field, and the thumb will be showing the direction of the magnetic force. Someone argue, what about this? Yes, you can curl, but you will be going through a big angle, right? If you keep it this way, the palm is facing away from you, then you will be going through a small angle. So that is what decides how to keep your palm. So the palm should be facing such a way so you are able to curl your fingers through the smaller angle between, so you can reach the magnetic field quicker. If you keep it like that, you have to reach the magnetic field in a very long angle. So then you see the thumb is pointing upward here for this particular example. So you get the direction of the magnetic force to be vertically up for this particular example. So you can see we have done this with the torque if in the mechanics. So you can write the equation as a complete vector equation like this. Q, the vector product or the cross product between velocity and the magnetic field. So the magnitude will be this because the definition of the vector product is Q is not part of the vector product. V and B is the vector product. So V magnitude, B magnitude, and sine of the angle between the two vectors will give you the magnitude. Direction will be determined by this right hand rule between the two vectors V cross B. So you get the direction. But if Q is positive, F will be the direction given by the right hand rule. But if Q is negative, it will flip the direction. Whatever the direction you get, it will be the opposite direction. So if Q is positive, no problem. The direction is from the right hand rule. If Q is negative, the direction is flipped by 180 degrees. So this equation as a vector equation will give you completely both the magnitude as well as the direction. So here we see it with this picture how it is done. So make sure you use your right hand rule, and you have to bring the V and B tail to tail, and you have to curl your fingers from V, starting from the V to the B through the smaller angle. Then the thumb's direction is the direction of the magnetic force. And after that, if Q is positive, you don't do anything. If Q is negative, you flip the direction. Now I can ask you to do a small quiz.